All right, guys, I guess you can hear my voice. Just confirm once. You all being able to hear me properly? Great, great. Okay. So, all your exams are over, Lakshya, Ushini, Elizabeth. Elizabeth, your exams are already over, isn't it? Or is it
No,
about to
sir.
get started?
I had 4 exams last week, and so I only have one exam next week.
You had 4 exams last week.
Yes, sir.
All right. So, how was your chemistry?
Sir, it was fine overall, but I
Mhm.
struggled a bit in organic.
In organic, in which chapter?
Sir, the conversions, they had given 3 questions, so it took quite some time to
Mhm.
solve them.
All right, all right. And what about you, Harshini and Lakshya? Go
Yes,
on.
the paper was good, but I got stuck in a few questions. We had discussed it in the DRS sessions also.
Okay. We have discussed about those questions already.
Yes, sir.
All right, fine. Right, guys. Yes, actually, you had a doubt. You told me, right? From which topic?
Yes, sir. So in the SWOTs reaction,
In the
um,
SWOT reaction. Yeah.
so for why D block elements are good fluorine donors, you said that it's because of the Z star. So I
Mm-hmm.
didn't really understand how higher Z star means a weaker bond with fluorine. Can you explain that?
So it's like what I tried to say over there is it's about the ionic character of the bond. All right. So you have seen that it's not about all the elements that we are taking. If you just focus on that, we are taking mercury, the fluoride of mercury, then we are taking silver, then what else? Basically, the D block elements, those are actually in the higher side of the D block elements, isn't it? Like not the 3D elements. I'm not taking any 3D elements right there. I'm taking the 5D elements or the 4D elements, isn't it? So actually what happens is there is something called relativistic effect that happens for mercury. From mercury onwards, that starts happening. For mercury, that is being seen, and for gold, that is being seen. So let's not talk about the technical terms right now. Okay, I'm trying to get away of that from that. Um, to be precisely, if I want to describe like what is the reason behind their very good fluorinating agent, the basic reason behind this is, as you know, they are high Z star. They have now, like in the lower side of the D block, they have really high Z star, right? More you go down, the Z star is even increasing because then we are adding the F block elements in there. So whenever the Z stars are actually increasing, their ionic characters are actually decreasing, and the covalent nature is increasing at the bond, isn't it? For AG systems or for AG systems, for them the covalent character of the bond is actually increasing. So that is what I try to tell over there. Like all the particularly all the metal fluoride, those are covalent in nature. They are actually very good covalent. I mean the fluoride donors, because what happens is when you're making the covalent bonds, and you can see there is a huge orbital overlapping between, if I talk about mercury and if I talk about fluorine. If it's an ionic bond, the orbital overlapping term is not coming in there, because ionic bond means all about plus and minus in there. But when it comes to the covalent bond, then comes the orbital and all those stuffs in there, right? Because covalent bond means it's gonna be formed by the overlapping of orbitals. And then when you understand that this is the covalent character is there, from there you can come to this conclusion that as they're covalent in nature, there is an orbital mismatching which is happening between mercury and fluorine, or silver or fluorine. which orbital mismatching is actually reason behind their bond breaking capability. All right. But again, there are going to be a lot of options out there. Like why mercury? Why silver? There can be a lot of options out there. Then again, that comes into the point of precision. Like let's say gold or any other compounds fluoride are giving me 90% product, and mercury's fluoride is giving me 95%. Okay, because of XYZ reason. That's why I am taking mercury fluoride. Are we getting this? Like it's all about now, it's come to the yield of the product. You can have a basic idea about it, and then it all comes to the research part, like where the yield is a little bit more, where the yield is a little bit less. Now, if you ask me, sir, what is the reason behind yield, then comes a lot of tons of factor in there, like the activation energy of the system, then the reaction medium of the reaction, then the temperature, the pressure which has been applied on it, then like tons of things are coming into that. All right. So let's not go into that complication. Let's just see that the bonds are very fragile. That's why they are comparatively better to right donors. You'd be able to see this thing again in group 18. Okay, in group 18 as well, you'll be able to see that these elements would be there again as a fluoride donors. You'll be able to see like group 18 when you be learning that inorganic chemistry. Then again, one more thing I wanted to tell you actually before I start this class today. So you can clearly see that we are right now going through the specific name reactions over the period of time. All right. So today I'll be taking and completing all the name reactions of alcohols chapter. I'm not only taking the name reactions, I'm actually pointing out to the portions which are actually written in the NCERT, and they can ask you the questions from there, which is underlying factors. Okay, we have to just pay some attention to understand those things. Okay, so those are there, but we might have overlooked them. These are the type of things we are going through. But I guess you have seen the JEE papers in this year. They were surprisingly, absurd. Okay, Lakshya, I've given JEE, right? In which shift were you there?
Sir, on 31st, the morning.
31st. Okay, how was your test then? How was your exam?
Sir, physics was easy, but chemistry was hard.
Chemistry was hard, isn't it? If you ever see the first February paper, Harshini, you have also given on 24th, right?
The 30th. The
Oh,
first
you
one.
gave on 30th. Oh, okay. So if you just check all the chemistry sections, surprisingly, they have just forgotten about all the weightage of the chapters and everything. Have you seen that? Just like 5 to 6 chapters are out there, those from where they are not even giving any question. No question from those 5 to 6 chapters, even more than 5 to 6 chapters. There are maybe 7 or 8 chapters. Those are comparatively easier that we consider that they are the marks gaining type of chapter. Let's say chemical kinetics for an example. All right, it's normal. The physical chemistry chapters, they're not even giving any questions from there. All the questions are coming from inorganic chemistry and organic chemistry. Then you have in organic chemistry, you have not normal questions. They're giving you bond migration and stuff in there. So guys, from JEE, you can take some ideas about the question going to come in NEET as well. All right, this is a good thing actually. The first good thing is the good students, those who are there with preparation, some sort of preparation, they would be solving, let's say, 5 questions. Others won't even be able to touch any single question in there if these kind of questions keeps on coming actually. In the inorganic as well, the type of questions that is coming in JEE, it's not as, let's say one question was there from coordination chemistry, but that also not from coordination chemistry. That is actually in your practical chemistry. Do you remember in organic chemistry practical, there is something called sodium nitroprusside test? Have you done that? From there, if you take K4 efficiencies and if you do and make it undergo sodium nitroprusside test, then you get a Prussian blue color. Okay, this is there in your syllabus, but you might not have done this in the practicals. But it's there in your syllabus. You might have written these things, or it's there in the book somewhere. They have asked that Prussian blue compound in there, and they're asking what is the formula of that. That's the coordination chemistry question they're asking. So all I'm trying to tell you is right now, focus a little bit more on inorganic chemistry. I will be giving you guidance for that right after the organic is over. All right, we have 2 more chapters. Then I'll be taking the inorganic. There's a particular pattern that is clearly visible in there. That is what you have to catch. If that kind of thing comes in NEET, we have to see it through first before it happens. JEE students, they have another chance. but you guys won't be having that chance, right? So we have to make the most out of it. Okay, so let's start talking about the organic chemistry right now. So from alcohols, what all important mechanisms are there, what are important reactions are there, and what are the underlying factors those are written in the book we might have not read it or somewhere there in that part. So this is going to be the point of discussion. Okay, guys, if you haven't watched the previous recordings that is there in the YouTube, you can just go and watch it. Okay, I have specifically taken all the name reactions and going very deep in there. Okay, all the possible type of questions that can be there. Okay, so do watch those videos first. For haloalkanes is over, and then we are in the alcohols right now. Okay, first discussion that will be there is about the hydroboration oxygen. But before I start talking about this, I'm going to show you the mechanism and all the possible questions that can come from here. First of all, guys, tell me one thing. Let's say I have a molecule which goes like CH3, CH double bond, CH2. I'm trying to add water in there. My question is it undergoing SN1 mechanism or is it undergoing SN2 mechanism? First, write it down in the chat. Okay, Lakshya. Or else I'm just adding HBr on it. Addition of anything in an alkene. What is the mechanism it is following? Come on. Consider that this question is there in your NEET exam. What would you answer? Okay, I got 2 answers so far. Elizabeth is the only one left. Be quick, guys. All right. So no answers from you, Elizabeth? No negative marking, don't worry. All right. See, this is one of the underlying factors which is out there. So I have seen that Harshini and Lakshya, you have answered this question. So I'll be starting from you, Lakshya. Why have you chosen SN1 as an answer?
Sir, my answer you can't see.
Oh, all right. I guess you're writing in the wrong account. Could you just write it in the other account right now?
Okay, sir.
In the meantime, Lakshya, carry on. Why are you taking SN1 as an answer?
So, you taught this 2 classes back. Marconico is SN1. So, like first it splits into H plus OH minus, and then hydrogen gets added, and then the most stable carbocation is formed, and then OH minus gets added to that. So it's SN1.
Great answer. All right. I would just check Elizabeth's answer real quick. Okay. Elizabeth, you have also answered as SN1. But do answer in the other account. Okay, that's not the account you should be answering here. Now, yes, so it is going to be SN1. And why did I discuss about this? 2 classes back when I was teaching you about the bond migration and stuff. All right. So it is SN1 reaction. And one more thing, you'd be able to see as it is an SN1 when they would ask you the addition mechanism. This mechanism is there in your book, guys, and they would ask you to write it in CVS. Okay, one is hydration mechanism, another one is dehydration mechanism. It is written in 3 separate steps. This is how you have to write those questions as well. So this is undergoing an SN1 mechanism, and that's why, guys, we always get the Markovnikov product. Markovnikov is always SN1. Now, Harshini, for you, you have also answered that as an SN1 reaction. Now, if I give H2O2 with HBr, that gives me anti-Markovnikov product, isn't it? So would you tell me in that case, what is the mechanism? Is it still SN1 mechanism or is it an SN2 mechanism?
Well, I think it is still SN1, but the radical stability changes in the mechanism. That's why the anti-Markovnikov product is formed.
Very good. So it's a SN1 kind of mechanism, and there also, guys, it is radical stability. So both Markovnikov and anti-Markovnikov, both of them are SN1 kind of reactions. Like Markovnikov is clearly SN1 reaction. Radical mechanism is SN1 kind type mechanism. Now, coming to the hydroboration oxidation. So when do we need it? When we need a terminal OH. Okay. Here we always get the internal alcohol. So when we need a terminal alcohol, that is when we need the hydroboration. This is something I guess all of you do know that. But you have seen lately in your practice papers, whether it's come from Ascites or from any other books you're giving it, you have seen that they're asking questions from the intermediates, isn't it? They're asking in hydroboration or any of the reaction they're picking up, and they're asking which of the following is the intermediate being formed in there. Now, to answer the questions like that, what is the intermediate of the reaction? You need to know the mechanism of the reaction. So for that, how the hydroboration oxidation mechanism goes on. See, first what happens is we take an alkene like this, and in there we are adding B2H6 in presence of THF. What is the full form of THF over here, Elizabeth?
Yes, sir.
What is the full form of THF over here?
Sir, I don't exactly remember. Does it end with fluoride?
No. Harshini?
That I don't know, but I know it's a solvent.
It's a solvent, right? Very good,
Yes.
Lakshya. That's correct. In BitSat, they asked this question. Okay, last year BitSat. So what is the solvent present in this hydroboration oxidation? And they have not asked you THF. They have given structures for this. So what is furan? Furan looks like this. What is THF then? Tetrahydrofuran. So all the double bonds are substituted by hydrogen. This is not outside of NCERT, isn't it? This is tetrahydrofuran. Okay, that's the solvent over here. Now, so B2H6 and THF. Now, this question is for you, Harshini. Why B2H6? Like, I'm not asking why is this reagent, but B2H6 is never really a molecule, isn't it? Boron's valence is 3. Like B2H6, how is it getting formed? Like, just enlighten me. Ashini, can you hear me?
Yes, sir. Am I audible?
Yes, you are audible. You are audible. Go on.
Sir, could you please repeat your question? Like why B2H6 is
Like-
used or why the structure?
Like B2H6 is never really a compound, isn't it? Boron's valence is 3. What is B2H6, sir?
B2H6 is a dimer. It is formed by the banana bonding that exists between two pH3 units.
Very good. It's a
As it
dimer
is
which is being
electron
formed
deficient, it has to.
as it is
Electron deficient.
electronically deficient, it undergoes this. Lakshya, she told us something about banana bonding. So, what is the other name of banana bonding, like with respect to the electrons or something?
So like some center electron bond.
That one. Go on.
Is it 2 center 3 electron or 3 electron 2 center? I'm not sure, sir.
Harshini, you're right. You just draw this molecule, Lakshya. This is BH. Then here, you remember the structure, right? Like this. Now, how many center do you see in here in the middle carbon in the middle system? How many centers? How many atoms are there? 3 atoms. So 3 center. But hydrogen cannot really have 2 bonds, right? Cannot really have it. So actually, the entire bond is having 2 electrons in there. So 3C2E, 3 center, 2 banana bonding. Great answer. Now, so actually, this is nothing but BH3. But guys, although I'm going to do the reaction with BH3, but I would never write BH3. I would write B2H6. Now, So what would happen if I add BH3 in here? So tell me now, if I add BH3, B, H, H, and H. This is the molecule, right? Now, this is where the hydrogen would get added up, and this is where the boron would get added up. Just a second. Yes. Okay. Now, what would I get from here? CH, hydrogen, CH2, B, H, H. Now you might ask me, so why is this getting added on this way? See, BH3 is getting added on in this way. Boron is not coming into the middle carbon just to avoid the steric influence. The steric effect given by this BH3, to avoid that, boron is not coming into the middle carbon. You won't be able to understand the steric effect right now, but after one more step, you'll be able to clearly see what is the steric effect I'm talking about. All right. So why is it going into the terminal carbon? Because the steric effect is there. Okay. Now what would happen is, now see, this is very important. Now three molecules like this are going to get attached. So like you can see, the way one hydrogen got attached to this carbon and the boron system connected to this carbon, in the same way, the boron is going to get connected like this with three molecules like that. So in the end, all the hydrogens are going to get substituted by this molecule. All right. So guys, it would be really very difficult for me to draw it over and over again. So I'll be considering this molecule as R. All right. So you know you are going to get this molecule in the end. B, R, R, and R. Okay. You'd be able, if you just open up here and said, you would be able to see this is written there. This is drawn in there. Okay. The molecule whole thrice. That is how they are writing it. Now this is what we're gonna have. Then what are they writing? Then they are writing H2O2 in presence of OH minus. Do you know what would happen with this? See, always remember the type of nucleophile you're gonna see today. It's one of the best nucleophile out there. We don't really make it in your level, but in our level, we have made it quite a few times. All right. Now see, H2O2 and OH minus together, they are gonna go like HOOH and OH minus, right? OH minus is gonna grab this hydrogen because OH minus is the base. Base looks for hydrogen. So that is gonna grab this hydrogen. Now, why is that hydrogen? Because that hydrogen is acidic. Oxygen is pulling the electron towards itself. So this bond is actually a little weak. It's an acidic hydrogen. So this bond is gonna break. So what is the product you would be getting? OHO minus and water. This is HOO minus. This is one of the best nucleophiles out there. Now this HOO minus, what would it do? What would it do? See, this HOO minus. Now Harshit just said that this boron is actually electronically deficient. You can clearly see that lecture. This boron is electronically deficient because of three bonds out there. All right. So boron complexes are always electronically deficient, isn't it, guys? Anything if I may, BCl3, BBr3, anything if I may. But there is one complex which is not electronically deficient. In chemical bonding, you have learned that. What is that complex? One complex made by boron is not electronically deficient. It's not a dimer, it's a monomer, but it's not electronically deficient. Very good lecture. Actually, just a small mistake. BF3 only. BF3 only. It makes back bonding. Very good, guys. It makes back bonding, and there's a partial double bond character in there. Now, as we are talking about back bonding, I would be taking a separate class of back bonding when we are done with all this thing in the capsule classes. But remember, back bonding is only present, only possible for the second period elements. For the second period elements. From the third period elements, you cannot see back bonding. That's why AlF3 or AlCl3 cannot show back bonding, but BF3 can show back bonding. And guys, both of them have to be from second period. It's not like one would be from second period, one would be from third period. That's not also possible. That's why BCl3 doesn't show back bonding. BBr3 doesn't show back bonding, but BF3 would show back bonding. So both of them have to be from second period. Only then the back bonding would happen. So I'm gonna give you more examples of back bonding later on. Okay, so this would be one of the agenda of discussion about the back bonding thing. Now, what would happen is, now there is a vacant orbital in boron, vacant 2p orbital, because boron over here is sp2 hybridized. You can clearly see that, guys, sp2 hybridized. So as it's the sp2 hybridized, there is a vacant pure p orbital present in boron, because we have 3 p orbitals, right? In order to make sp2 hybridization, you need only 2 p orbitals out of them. One p orbital is completely free on there. So this is the p orbital which is completely free. Now what would happen? This O minus would donate the electron to this p orbital. And guys, what would happen? As a result, you would get B R. Let's just draw the R on the top side. R, 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 then O, O, H, and as it's a coordinate covalent bond which is happening out there, guys, so it would be a minus charge on the top of boron. Are we clear? Now, what's going to happen next? To remove the minus charge from the top of boron, this R would make a rearrangement and it would go to the oxygen and take the OH out as a. If you don't understand this, guys, you don't have to put pressure on yourself. All I want you to do is you just write it down in your copy and keep it with you. Even if this kind of question ever comes, you would feel like, okay, I have seen this somewhere. And that is all I need. All right. Now, from here, what is happening? B, O, R, R, R. Now, guys, there is a lot more H2O2OH minus out there. So this reaction would happen 3 times. And you know what is the final product that we would get? BOR, DOR, BOR. Okay. This would be happening 2 more times. And we're getting BOR, OR, and OR. So far. Okay. Now, once we are done with this so far, then if you add water, then the water molecules would come and replace the OR from there. So you'd be getting BOH, OH, OH, and the OR groups would go out with taking the hydrogens of water. So ROH, 3 molecules of ROH. So in one hydroboration oxidation, guys, you get 3 molecules of product. Again, another statement you need to remember. This is there in the NCERT, that the stoichiometries are given. So they can anytime ask you a question like this, like from hydroboration, how many one mole of B2H, like from one hydroboration molecule, how many products are you going to get? Okay, how, like whatever way they can arrange this question. So they're going to get 3 alcohols that you're going to form. Now, what was the R molecule, guys? I told you before, the R molecule is CH3, CH2, CH2, this thing with OH. That's my final product, carbonyl alcohol. Okay, just keep it with yourself. If they ask you about the intermediates, anything related to this question, so that you get to know about this. Go ahead, Harshini. Okay. Lakshya, no doubts? Should I move on? Great then. Where is Elizabeth? No, she got disconnected. Okay, now. So now I'll be talking about Kolbe's reaction. This is something I guess all of you are very much familiar with. So Harshini, tell me, what do you remember? What was the Kolbe's reaction?
The phenol is first made phenoxadiene, and that when treated with carbon dioxide H plus gives salicylaldehyd.
So I would be using NaOH with phenol, isn't it?
Yes, sir.
That would be taking the OH minus taken up like O minus Na plus, not occupying the salt anymore. So are we saying phenol is acidic in this question?
Could you please repeat?
So are we saying phenol is acidic in this question?
Yes, sir.
Is it more acidic than acetic acid or is it less?
Less than acetic acid.
Are you sure about that? Because phenol can make a lot of resonating structure in there.
Yes, sir, but acetic acid forms two more stable resonance structure compared to that.
Yeah, I just want that word right now. Acetic acid makes two
Equivalent resonating
equivalent
structure.
resonating structure. Exactly. That term is needed. The equivalent resonating structure. That's why that is more stable. What do you mean equivalent resonating structure over here, Lakshya?
So like similar.
Similar looking.
Yes, sir.
Yes. So before and after, if you look the same, that is called equivalent resonating structure. So that's comparatively more stable. Whereas when you talk about phenols, you would be able to see only one of the resonating structure is aromatic. All the other structures are not aromatic, isn't it? They have to break the aromaticity for those. So that's why it's comparatively stable. That's a great answer. Phenol would be definitely more acidic than any other alcohols, right, guys? Any other alcohols, if I compare that. All right. Now, this is going to be the product that I'm going to get. Now, after that, what do I have to give over there, Harshini?
Carbon dioxide and H plus.
Carbon dioxide and H plus. So what would be the product then? Salicylaldehyde. This.
Yes, sir.
Daksha?
So it's acid, right? Like COOH.
All right. That's right. It's going to be salicylic acid. Isn't it, Harshini? Now, what is the mechanism here? And I have a question for you. See, have you ever asked yourself? I guess I have talked about this though, but I will be still asking you. Have you ever thought about this? Generally, the para is the major product, isn't it? But have you noticed for this reaction, ortho is the major product? Have you? This is the ortho. How is it the major? Not only major, they're saying the only product out there, almost only product. Very good, Rishi. That's right. Laksha? Right answer. That's hydrogen pumping, right? Okay. So what is really happening over there, guys? Then you have carbon dioxide. Then what happens is the resonance and it backs on the carbon. The bond breaks up. We have discussed about this mechanism in the class as well, right, Laksha? Did we or did we not? Yes, we did. CO minus, then we have double bonded O. And the hydrogen goes back to restores the aromaticity. And if we just hydrolysis walk up, we're getting, in terms of carboxylates. All right, great. Now the question that I'll be asking you is, this was the mechanism, right? Now you tell me, if I do the Riemann reaction, I mean the Kolbe's reaction, giving NaOH, then I'm giving carbon dioxide, and then I'm giving D2SO4 in presence of water. Okay, not giving H2SO4, I'm giving D2SO4. Then what would be the product? You have 4 options like that. Like, not really, I'm not going to give you 4 options, but in the question they'll be giving you 4 options. So guys, what are they asking you, right? they're asking you to track the hydrogen. Track the hydrogen from the H2SO4. They can give you D2SO4 H2, or they can give you H2SO4 D2. You have seen this kind of question coming as well. So try to figure this out. Just totally forgot the year of the question. But anyway, this is the PYQ, all right? It's not a normal question that I'm asking. Very good, Harshi. Exactly, Laksha. Very good, guys, both of you. If you would be getting COOD. See, I'm not really teaching you these questions right now. I'm teaching you the type of question that they can ask you. So whenever you'd be learning this chapter or any chapter in organic chemistry, make sure these are the different types. So you have to just, they would change they would just change one reagent in there. Like instead of H2SO4, they can suddenly give NaOH in there. Then what would happen? These kind of things you have to just think about it. So for that, you just have to look into the reaction mechanism each and every time. So if they give NaOH suddenly, then what would happen? Instead of H2SO4, then this molecule would keep on, would stop, this reaction would stop at COO minus. That's it. Because the last step is where the hydrogen is coming to carboxylic acid, right? So when you have a base, the carboxylic acid won't be having its hydrogen because the base would be taking it out in that way. Okay, so depending on it, like if they give you an option, there are minus charges in here as well in phenol acid, then that would be the better answer because both the hydrogens are acidic. So you have to just keep your eyes and head off when you're learning the any mechanism in this way. All right, and they would do like this. They would keep everything same, but they would just change one reagent. And this is the exact kind of question they have asked in change. They have given you Gabriel Thalimide synthesis, and in the end they have changed the molecule. Like everything is same, but in the end, what happened is that after 3 or 4 steps, you realize that the last reagent is not the same. Now, what happens is the people, those who are seeing that okay, this is Gabriel Thalimide, they'll just stick it up. And those who doesn't know about that, those who are very cautious, they're doing the mechanism, but in the end, they would get stuck. So in this kind of a question, what would happen is you have already lost your 2 groups solving the question. And in the end, you realize that I don't know that. Yeah.
Sir, if in the third step, D2SO4 and D2O is given, so in the product, will it be OD and COOD?
Then what would happen is the COD would be there. Okay, and the OH would become OD, yes. The OH would also become OD and COOD would be there. That's correct. Very good. Okay. If instead of water, if you give D2, this was O minus. It became OH because of the water. So it would become OD as well. Good. And they can give you one more type of question, actually. They can isotopically level oxygen as well. Like oxygen's isotope is O18 is there, right? So they can give you O18 and they can ask you to find out what is O18. It's very simple right now. Right now, it's very simple. You can just figure it out like it would be in the COO, right? That's not really problem. But they can isotopically level anything. Like I'm showing you D2 or D2SO4, they can just isotopically level some other element in there. Okay. Make sure you got that covered. Now, coming to Riemann reaction. Okay. Now, tell me, Laksha. For lime-bitumen reaction, we will start with phenol. Then what are the reagents that we have to give?
So CHCl3 and
And NaOH or KOH, right? Okay. What is the intermediate that's going to get formed? What's the name of the intermediate? That's right, Lakshya. And that's right, Rashmi. We're going to get dichlorocarbon. That's correct. What is the hybridization of the intermediate that is getting formed? Both of you are correct. What are the number of electrons present in that intermediate? How many electrons are there? Yes. I mean, yes. How many lone pairs? That's correct. One lone pair. All right. I'm not going to stop unless you give up. Where are the lone pairs? Is it in the sp2 orbitals or is it in the pure p orbitals? Dichlorocarbon is sp2. You just said, right? Is it in the sp2 orbital or is it in the pure p orbital? No, that's wrong, Harsh. Both of you are wrong. Are you discussing together? When you're right, both of you are right. When you're wrong, both of you are wrong. See. So finally, you had to give up. So we get dichlorocarbon in here, right, guys? Now, what happens is carbon is sp2, right? So as it is sp2, there is one orbital here, and the other orbital. sp2 means 3 orbitals out there, right? So one of sp2 orbital is this one. The other one is this one. This is the third sp2 orbital. Now, there are two types of carbons out there. One is called singlet carbon, another one is called triplet carbon. See, singlet and triplet are overhyped. These are really very simple. What actually happens is, how do we calculate the magnetic moment of anything? You go like number of unpaired electron. Oh no, you don't really know this. So actually, how do we calculate the multiplicity of spin? Multiplicity. It's right. Like number of unpaired electrons, if the n is equals to the unpaired electrons, then 2n plus 1. This is the spin multiplicity. Okay. So as you can see, in singlet carbon, why do we call it singlet carbon? Because there is no unpaired electron in there, present in there. Right. So number of unpaired electron is 0. So for singlet, why do we call it singlet? Because the spin multiplicity is 1. So this is the multiplicity which is 1. That's why we call it singlet. So this is one kind of carbon out there. The other kind of carbon out there is called triplet carbon. What is this? This is my pure P. What is this? This is my sp2 orbital. Now the other kind of carbon that can be there is one electron in the sp2 orbital, one electron in the pure P orbital. Now, how many unpaired electrons are there? 2. So what is the spin multiplicity coming then, guys? 3, right? 2n plus 1. Just a sec. It's coming as 4, 5, isn't it? I just messed it around. Just a second, guys. Just start over again. One more time. See, n equals to unpaired electron. Okay. It goes like 2 into n by 2 plus 1. This is actually n plus 1. N by 2 is another value called s. So it's just n plus 1. That's the spin multiplicity formula. So n plus 1 means this is 3. 3 is the value. So that's why we call it triplet. Right? These are the two types of dichlorocarbons out there. Now, when do we get singlet carbon? When do we get triplet carbon? That's the last thing that you need to know. Singlet carbon is when, let's say, the carbon is getting formed in the reaction and you are making the reaction happen. Okay, that is singlet carbon. Singlet carbon means it's just the first carbon which is going to get formed. Whenever you make a carbon, whatever the carbon is, that would be always singlet carbon. Now, if you give some time to it, if you give it some time, then it would turn into triplet, because triplet is more stable than single. Because you can clearly see in one orbital you have two electrons, electron repulsion is there, but in triplet that thing is not there. The triplet is more stable comparatively. So when is triplet carbon gonna form? When you give the reaction some time, singlet would turn into triplet. But if the reaction is getting formed immediately, like Riemann reaction, it's singlet carbon. All right. Now, that's why what happens is, I'm afraid no one is going to ask you any questions from singlet or triplet carbon, but there's no harm in knowing this. It's not really a very big topic that I told you. Now, so that's why, in class 11th, we have this. It's not really like completely not there. In class 11, what they do is there is one or two reactions of carbon in there in hydrocarbon chapter. Just check it once. If I'm not, I mean in GOC chapter, just check it once. If I can be wrong, it cannot be in there in the NCRT, but this thing is actually being taught in class 7. See, carbon is the only intermediate. See, carbocation is something who can take electron. Carboanion is something who can give electron. Carbon is the only intermediate who can take as well as give. If you give electron, it would be taking the vacant P or P. And if this carbon has to give electron, the Laksha it would be giving from a sp orbital. That is the speciality of carbons. In Riemann reaction, what happens is, as you have an electron donating element, so it is taking electron. And the molecule is going to form C, Cl, Cl minus. That's why there's a minus out there, because the coordinate covalent bond. Then this CCl2 minus is going to take some water from the outside and would become CHCl2 minus, CHCl2. Some water from the outside. Okay. Now, if they turn it into D2O, then CdCl2. Right after that, you have to give NaOH. Now, what would happen with NaOH? NaOH would give you OH minus. Now, what would OH minus do? Nucleophilic attack, taking the Cl out. What is the reaction going on? That SN2 reaction. If it is OD, then OD would be there instead of Cl. CH, OH, and this reaction happens twice. So both the chlorines are going to get substituted. Then I told you in one molecule, one carbon, two OH molecules cannot be there. You have to remove water, right? So the final product you're going to get is CHO. Again, why is the ortho major product? Because of the hydrogen. Oh, that's a very unstable situation actually. What happens is, Lakshya is asking me, sir, why the two OH molecule cannot be there in one carbon systems? Because see, always remember, water is the most thermodynamically most stable element in the earth. Thermodynamically, most stable element in the earth. Nitrogen and water, these two are things. In diazonium chloride, you have seen, whenever you heat diazonium chloride, nitrogen just goes out very easily. Similarly, water is also a thing. If you have seen this quite a few times. Whenever there is a reaction and water can go out, in the aldehyde ketone carboxylic acid, you have seen this every single reaction. Whenever there is a chance of water going out, water would go out first. So water is thermodynamically one of the most stable elements, not one of the most stable element in the earth. So that's why whenever there's a chance, it takes out water, every molecule. Are we getting this? See, there cannot be any other underlying factor after all this discussion that we are having right now. There's nothing in there anymore. These things are actually there in class 11th and 12th. They give these things. And then they are going in deeper down when you go to the bachelor degree. All right. So these are all the things that I have learned in my bachelor degree. So no one really from class 11th to 12th, no one really understand all these things there, unless and until it's being taught separately. One last thing before we end this class up, dehydration of alcohol. I guess you guys are aware of it. What happens when the temperature is being changed? So, Lakshya, tell me what would be happening on the top situation. Ether, right? Ester. Carboxylic acid. Anything? Or none of the above? That's correct. Okay, see if that helps. Now you are giving me options. So one of them is alpha. Which one is alkene? That's the question. See, right now I'm going to tell you something, which is not only this question, is going to help you later on as well. Always remember, whenever there is an increased temperature, it's always elimination. All right. Once I told you this, because it's completely related to thermodynamics. See how interesting it is. Let's say you have this molecule, right? You have given concentrated H2S. If you do an elimination, then what would happen? You'd be getting alkene. What would happen, guys? So first, the concentrated H2SO4 would break into H plus and HSO4 minus. This mechanism is there in your NCERT, and they do ask this question: remove of water. Then this lone pair takes the hydrogen, and you get OH2 plus. Now the HSO4 minus molecule, it goes and grabs this hydrogen and make it undergo E2 elimination. E2 elimination. Just like I said, it is E2. So what are the products that you're going to get in that? You get CH2, your concentrated H2SO4 back, and you get a molecule of water in there. Yeah, these three products is what you're going to get, isn't it? You're going to get three products. Now let's say you're doing a substitution reaction. Let's say there is CH3, CH2, OH, and you're doing any kind of a substitution reaction. CH3, CH2. Remember, this is going to save you from many unknown questions out there. This. Now see, is there any change in deltas in this reaction? See, there were two molecules before, two molecules after. So not really any change in deltas, right? But if you see here, there is a delta S positive, right? So now you tell me, if I go like delta G equals to delta H minus T delta S, applying that, when for elimination reaction, the delta S is positive. So when you increase the temperature, delta G would be more and more negative. So elimination reaction always occurs when you give a temperature in there. So that's why the first product, when you have more temperature, you get elimination. Whereas in the second product, on lesser temperature, you get a substituted answer. You get a substitution, isn't it? Ether is a substitution, SN2 substitution. It is written in the book, SN2 is mentioned in the book. There's an SN2 substitution. That's why in lower temperature, you get SN2 product. Higher temperature, you get eliminated product. See, always remember this. Why is it so important? They would give you a molecule and they would give you an anion in there. Okay, listen to this very carefully. Let's say they would give you a molecule like this. And they would give you an anion, A minus. They would ask for a product. Okay, there are two possible products that you'd always get. One is eliminated product. One is substituted product. Always. These two things would be there. Because whenever there is an anion, every anion can act as a base as well as nucleophile, which is only the glimpse of it only you have seen in the H2SO4, this question. Every anion is actually capable of doing this. The moment they put an arrow triangle on the top, it's elimination. If they don't, it's substitution. Okay. Substitution elimination as well. I'll be talking about this. Like these are some special extra topics. Substitution elimination, substitution versus elimination. And there is something that I would just teach you as a buffer, which is called NGP, neighboring group participation. These two things. Already, I have taught you the bond migrations. So you are not supposed to have any issues with bond migration. But before we end this entire thing up, like the organic section up, I'd be doing some of the example of this. SNI, Harshini, I just forgot to teach that the other day. I have it with me. I would be like the first reaction. That's a very good point that you talked about. SNI, do you know which one is SNI reaction? In our syllabus, which one is SNI reaction? The SO2Cl2, chlorination by SO2Cl2, alcohol to alkyl halide, SO2Cl2, that is SNI reaction. I had that, no, in the last class only I was trying to teach you this. Let me show you. I'll be taking this thing in the next class. I just missed it by somehow. There you go. SNI versus acetate. I just missed it somehow. And as the name reaction discussion we are having, so I am not really being able to go back in there. But anyways, I'll be talking about this in the next session for sure. All right. So guys, don't miss the next session if you are free. Okay, I'll be taking one more name reaction is left in there for alcohol. Then we'll be moving on to aldehyde ketone carboxylic acid name reactions. All right. So that will be it for today. Bye.
Thank you, sir.
Thank you, sir.
Welcome.